Hi class, welcome to the next section. We're starting chapter 12. We're going to start with sequences and summation notation. This entire chapter is about sequences and series, basically a set of numbers that follow a pattern, right? So this is very important in calculus, especially at the end of calculus 1 and the beginning of calculus, or really all of calculus 2. This is a very important topic, okay? So again, a sequence is just a list of numbers that follow a pattern. And what we're interested in is, what is that pattern? And what happens when we add all these numbers together? That's actually a very important topic to us, especially again in calculus. Okay, so most of the time we want to know what the general value is. The general term in a sequence is called the general term. Okay. And that's what we're interested in. So let's start with some very basic, very easy sequences to begin with. I'm pretty sure all these sequences that you're going to see right now are things that you've seen before, but maybe you haven't thought about them in the way that we're going to describe them now. Okay. So our first sequence is the set 1, 2, 3, 4, and so on. Okay. Obviously, we know what the sequence is. We call it the natural numbers or the counting numbers or the positive integers, but we haven't talked about it as a sequence of numbers. So here, the general term is just n. Okay. We always start off at 1. Okay. So the first term, we plug that into here, we get out 1. For the second term, we plug 2 into the general term, which is n, so we get 2, 3, 4, etc. Okay. The next sequence is 2, 4, 6, 8, the even positive integers, right? So this sequence can be described generally as 2n, right? The first term is 1 times 2. The second term, 2 times 2. The third term, 3 times 2, 4 times 2, 5 times 2, etc. The next sequence is 1, 3, 5, 7. This is also a generalized term, although it's not as common as A and B. So here we can see that the difference between everything is 2, but this is the odd numbers. Okay, and so the general term for the odd numbers is 2n minus 1. So for the first term, if I plug in 1 here, I get 2, minus 1 will be 1. For the second term, if I plug in 2, I will get 4, minus 1 will give me 3. 3 times 2 is 6, minus 1 is 5. 4 times 2 is 8, minus 1 is 7. So we can describe the odd numbers, positive odd numbers, with the general term 2n minus 1. For the next sequence, we have 3, 5, 7, 9. So it's the same sequence of numbers, but without 1. So now we have to say, well, how do we describe this? Because I can't describe it as 2n minus 1 because I would have 1 first, right? So here the general term is 2n plus 1. 1 times 2 is 2, plus 1 is 3. 2 times 2 plus 1 is 5. 3 times 2 is 6, plus 1 is 7. So here it's a little bit different, right? So here just changing the minus to a plus gives us a whole different sequence. Okay. The next one is 1, 4, 9, 16. Right, can you see what the pattern is? Each term, I'm taking the value that it is, the first one, the second one, the third one, the fourth one. I'm taking that value and I am squaring it, right? This would be n squared. So we don't always have to add and subtract things or multiply things. We can do literally any operation. I can take square roots. I can say 1 over my number. I can say 1 over my number squared. I can say 1 over my number minus 1. I can do any sort of operation to get a sequence of numbers here. Okay. The general term we call a sub n. That's our general term. Because any nth term is found by just plugging in whatever index we're on into that general formula. Okay. The first term is the a1 term, right? Because n would be 1. a2 is the second term, etc., etc. It always follows this notation, right? This is the standard for a sequence. Okay. If I want to plot a sequence, I just plot them in order, right? So the first sequence, I go up to 1. The second sequence, I go to 2. The second sequence, I would go to 3. The second term, I would go up to 4. So in general, I can plot this as 1, 2, up to n, right? And then that term. So for instance, if I wanted to plot this sequence, I would go 1, 1, 2, 3, 3, 5, 4, 7, right? I would plot these, whatever number they show up in the sequence is the order that I graph them. So when I'm graphing a sequence, I'm literally just plotting one number at a time as they show up, okay? Sometimes we plot sequences, a lot of times we don't. We do when we want to see if they kind of level out to something. That's something that you'll see in a higher level class. We might do that here once or twice, but it's not something that's very, very general when we first start describing these things. Definitely we'll see that in calculus. So that's why I'm not elaborating on this too much, because it's not particularly important at this point. But once we get into calculus and we start talking more about limits and things like that, then yes, we will see graphs of sequences and the like. Okay. So this is one way to describe a sequence, is general term. Okay. Another way to describe a sequence is recursively. Recursively means I'm going to talk about the next term, or the term that I'm on, by its relationship to the previous term. Okay, so it's really about how do I find the next term, my next term, based off of the value before it. Okay, so let's find recursive examples for these sequences that we have here. Okay, so just remember what they are. One is the counting numbers, then the evens, then the odds, and then the odds kind of shifted by 1, and then the squares, right? So if I want to define this sequence recursively, right? So this is how I define it with this general term as just n. If I want to define it with its recursive definition, you have to talk about where you're going to start, right? And then how do you find the next terms after that? So if I start at 1 and all of my next terms are based off of the last term plus 1, right? That's how we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Whatever value I was before, to get to the next one, I just take the one I was at before and I add 1. Okay. Here, the same thing. I'm going to start at 2. And in order to find my next term, I'm going to take the term I was at before and I'm going to add 2 to it. Right? Same thing here. I'm going to start at 1. And in order to find my next term, I'm going to add 2 to the last term. So you see how changing the starting point, but the same recursive formula, gives me 2 different equations. I can have the same definition here, because here everything is changing by 2 as well. So here, my first term will be 3. And my next term will be found by the last term plus 2. So B, C, and D have the same recursive formula, but a different starting point. One is that starts at 2, one starts at 1, one starts at 3. But obviously they both change by 2 each time. So the recursive formula is the same, just a different starting point. Okay. Here now this is going to be a little bit different. Okay. Because yes, I'm going to start at 1. But my recursive formula is a little bit harder to find because I'm not following a steady rate of change, right? Here, my rate of change was constant, right? I'm always changing by 1, always changing by 2, always changing by 2, always changing by 2. Here, I'm not changing by 2. My rate of change is changing as I go from one value in the sequence to the next. So I can define this as starting at 1, and each next term is the term that I was before, plus 2n minus 1. The difference here is 3. The difference here is 5, 7, so forth, right? So I take 3, 5, 7, so forth. So if I'm starting at 1, I am now on, for n equals 2, right? In order to find n equals 2, I take 2 minus 1, so that's 1, plus 2 times 2, which is 4, minus 1, which is 3. So 1 plus 3 would give me 4, and so forth, right? So that's how I find my recurrence relation, by looking at the difference in values from one to the next. Okay. Sometimes it's not that easy, but you know, for the ones that we have here, this is how we define the recurrence relations. A common sequence, the most popular one really, is called the Fibonacci sequence. Okay, you've probably heard about it, but maybe you don't know what it actually is. So the Fibonacci sequence is a sequence of numbers where you find the next term in the sequence by adding the one you're at with the one previous. Okay, so I don't have one before, so 1 plus nothing is 1. Then 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5, 13. 13 and 8, 21. So you're adding the number you're on with the one previous to get the next number, right? And that's what the Fibonacci sequence is. Okay, so each term is found by adding the two previous terms together. It is a very, very common sequence. It's very important. It has a lot to do with what's called the golden ratio. It's found in nature everywhere. Okay, tree branching patterns can be described with the Fibonacci sequence. So branching patterns meaning as you go up one notch on a tree to the next notch on the tree. So generally a tree will have one branch as you move up from the ground to its trunk. And then as you move from that branch up to the next branch, you will see 2 branches off from that. And as you move up from there, you will see 3, and then so forth and so forth. So branching patterns in trees generally follow the Fibonacci sequence. Okay, same with flowering patterns. So if you look at artichokes, Brussels sprouts, certain flower petals, the interior of a sunflower, right? The way that the seeds are dispersed are kind of located in the center of the flower. Those follow the Fibonacci sequence. Okay, the growth pattern of a snail shell or a nautilus shell, right? Spiraling arms of a galaxy. So they're seen everywhere in nature. Hurricane formation. Okay, facial symmetry follows the Fibonacci sequence, etc., etc. There's lots and lots and lots of applications of this, right? So in order to represent this graphically, let's look at rectangles, squares really, with areas following our Fibonacci sequence. So here, this would be a unit square. If we attach to this another unit square, right? So 1 times 1 is 1. Notice now that this has 2 units. So let's attach to this a 2 by 2 square. Okay. Now this has 2 and 3 units along, right? So let's attach a square that's 3 by 3. Now this is 3 and 2, so that's a 5 unit square. So we'll attach a 5 by 5. Now we have 5 plus 1 plus 2, which is 3. So now we have 8. Okay. Now we have 5 and 8, which is 13, and so forth and so forth. So if we connect these corners with a spiral, we get our Fibonacci sequence, right? So obviously this already looks like a snail shell, right, or a nautilus shell. If you think about our galaxy, it has a spiral pattern, right? Flowering patterns, as flowers grow, they grow in a spiral fashion that follows the Fibonacci sequence. So this is kind of everywhere, right? So this brings us now to what's called the nth partial sum. It's pretty much exactly what it sounds like. We add up our sequence. We add the values in our sequence. Okay, so a partial sum is the sum of the first n terms of a sequence. That's the nth partial sum. So the third partial sum would be the sum of the first 3 terms in the sequence. So we denote the ith partial sum as s sub I. Okay, so if we have the sequence, for instance, a1, a2, a3, up to an, and so forth, then the first partial sum is just that first term. The second partial sum is the first 2 terms being added. The third partial sum is the first 3, and so forth and so forth. The nth partial sum is whatever index we have for n. Okay. We can make a sequence out of these sums, right? This is a number, this is a number, this is a number, this is a number. We can write these as a sequence. Okay. So example, let's find the sequence of partial sums for an equals n squared. So the first one is 1. Okay. The second one is 1 plus 4. So remember, this is as squaring each term. So 1, 4, 9, 16, 25, 36, etc., right? So the third partial sum is 1 plus 4 plus 9, or 14. The fourth partial sum is 14 plus 16, basically, because I know these three add up to 14, so I just gotta add the next one. So it'll be 30, and so forth. So if we write this as a sequence, 1, 5, 14, 30, it's actually pretty hard to find the pattern here, but this is a well-known sequence actually. So it's easy for me to find out what the formula is for this. So it's 16n times n plus 1 times 2n plus 1, right? Not all sequences of partial sums are hard to find for the general term. Okay, in fact, the next couple sections, that's what we deal with. How do we find the partial sum? Actually, that is one of the big things we're going to talk about. But also, just how do we find general terms in general, right? So there's kind of two categories at the moment for sequences, and we're going to explore those in the next two sections. And we're going to talk about how to find the partial sums with the formulas, things like that. Okay. So for this sequence, this is what the formula would be. Okay. So now let's talk about summation notation, because we're talking about adding stuff together. So there is a notation for adding stuff. If you've ever taken a stats class, you'll see it in statistics. Again, you'll see it in calculus 1, and it is everywhere in calculus 2. Okay. Actually, every class after this, you're going to see it for whatever math you take. So the summation notation, this is called a sigma notation. That's the other name for it. Okay, because this is the Greek letter sigma, capital sigma. So we have k equals c to n of ak. And what this is AC plus AC plus 1, AC plus 2, all the way until n. So we're going to describe what all these things mean. Okay. C is my starting value. A lot of times it's either 0 or 1, but it can truly be any value I decide to start with. This is called my index or my counter. Okay. So I start with whatever this number is and I substitute it for k. Okay. Then I go one up from that and I substitute it for k. And then I go one up from that, so forth and so forth. So this counts by 1, and whatever value it is, you substitute into here. And each time you have a term, you add it together. N is where we decide to stop. Okay. So k is my index counter. Okay. C is my starting index, is where I start at. N is my ending index, is where I stop. And A sub k is the general form of the terms that we add together. So those general terms, those general forms that we had, that's what we're looking for AN, or AK I should say. So let's do an example. So let's find this partial sum, right, from k equals 0 up to 4 of 2 to the k minus k. So what we do is every time we add in, we substitute k equals whatever value we have here, starting from 0 and ending at 4. So if I want to do this, my first term, I plug in 0, so that'll be 2 to the 0 minus 0. Now I'm at a counter of 1, so I plug in 1 everywhere, 2 to the 1 minus 1, and I'm going to add those terms together. And then I'm going to substitute in 2 for k and add that, and 3 and 4. So notice, even though it starts at 0 and ends at 4, that means there's 5 terms here. If I started at 1 instead and ended at 4, I would have these 4 terms, and this one would not be here. So this is where I start, this is where I end. Okay. So when I plug this in, this is 1. This is 2 minus 1, which is 1. 4 minus 2 is 2. 8 minus 3 is 5. 16 minus 4 is 12. So if I add all these together, I get the value 21. So the sum of this series, this is called a series, the summations are series, the sum of the series is 21. Okay. Now the thing with series is that I can change my counter and I can change my index k here so that I start somewhere else, but I have the exact same sequence of values. Okay, so as an example to that, let's say that I have k equals 1, so instead of starting at 0, I start at 1. and I go up to 5 instead of 4, so I still have the same number of terms. And notice what happens. If I shift this up by 1, I'm going to shift k by 1 everywhere as well. So 2 is going to be, instead of k, I'm going to have k minus 1. I moved up by 1, so I'm going to start this one less. Okay. So when I plug in 1 here, I'll get out 0. When I plug in 1 here, I'll get out 0. I'll have the exact same sequence of values. So here all I did was distribute this negative sign, so it looks like this. Okay. So this sequence is the same as the one I started with. This sequence is also the same sequence. Okay. So I can shift my index and get the exact same thing. Right. So summations are kind of funny that way. Is you can have, multiple representations of the exact same value sequence of numbers. We're not going to get too much into that. That's again more of an advanced thing, but I just want you to be aware of that you can have the same sequence under different representations. So properties of sums, there's actually lots of properties of sums. Most of them are not necessary for this level of class. If this interests you, you can look at the different properties of sums by looking at a calculus textbook. A calculus textbook will have all of the properties of sums, which will be used for other things at that level. But for right now, the important properties, there's only 2 of them, which is a constant times all of my values is the same as me pulling out that constant. Okay, because think about it. I'm having some number, maybe 5 times everything, and I'm adding them all together. That means everything I'm adding together has a multiple of 5, a common factor. So I can just pull out that common factor times my sum of values. Okay, this is actually a very useful property. The other property is that if I have addition or subtraction within my general term, I can actually separate that into 2 separate sums. Okay, being either added or subtracted together depending on what formula was going on the inside.